Homework last night, page 523, 6 to 12, except for number 11. Any questions with that? 12? Caitlin? 10C? I got 10C, I got 12, I got, okay, just 10. Got 10 and 12. 9B. 9B, 10, and 12. All right. 9B says, compare the distribution of charge after a small negatively charged metal sphere momentarily touches a larger neutral metal sphere. Some people, I think, were confused just with the wording of this, the distribution of charge. It just means how the charges are distributed, how the charges move about, where they are on the surfaces of these different materials here. We've got a small negatively charged metal sphere touching a larger neutral metal sphere. What's going to happen? What's going to happen here, Patrick? Yeah, you're going to get electrons moving to the right-hand side here. Now, is it going to be evenly distributed? Is it going to be an equal amount of charge on the left one as it is on the right one? In other words, are they going to completely balance out? One of the things that we said in class is that we normally assume that these objects, when they touch each other, are equal size, equal shape, and therefore they balance out equally, right? But if they're not equal size and not equal shape, then they wouldn't balance out equally. The reality is this big object can hold more charge than the little object does. So in this question, what they're getting at here, I think, is that this big one is going to be able to hold more charge than the little one. The big one will end up being more charged negatively than the little one will be. Does that make sense? Now, I doubt you'd encounter a question like that on a test. Every question that I've seen, I think, on a test at this time has involved two objects that we can assume are equal size, equal shape, so that they balance out perfectly. If it's not meant to be that, then they're going to give us some indication that it's not a safe assumption to make. Okay? They're going to give us an indication like, hey, one of them is bigger than the other one. Okay, if they tell us one's bigger than the other one, they must mean that to mean something. They must mean that to be significant in some way. Always remember, the one that's bigger can hold more charge than the one that's smaller. Right? Number 10 says a negatively charged ebonite rod is held near the knob of a neutral electroscope. Explain what happens to the leaves of the electroscope. Well, we know what happens to the leaves of the electroscope, right? They spread apart. But why do they spread apart? If this is the top of the electroscope, this is the copper rod that hangs down, and then these are the two little metal foil leaves of the electroscope. Then when we hold a negatively charged ebonite rod, or negatively charged anything else for that matter, nearby, that's going to push negatives down from the ball of the electroscope down into the leaves. What's going to happen to the leaves? They're going to spread apart. Why are they going to spread apart? Because they have just negatives on them? No, they're going to spread apart because they have more negatives than positives on them. Still the same positives that were there before are still there, but now we've got some negatives on there as well that we didn't have before, giving us a net negative charge. Therefore, they separate. C, explain why moving the ground first. B. Explain what happens to the leaves of the electroscope if the other side of the knob is now grounded while the rod is still in place. We talked about this a little bit, right? Yesterday, I think it was. What happens? These electrons aren't going to go down into the leaves. The electrons are going to go down into the ground. What's that going to do to the bottom? Well, the protons are still where they were, but the electrons are being pushed down into the ground. So although the leaves still stay spread apart, they're now going to be positively charged spreading apart. And finally, C, explain why we're moving the ground first and then the rod will leave a net charge on the electroscope. Let's cut that ground. We've left a net charge on the electroscope because the extra charge went down into the ground and it has no way to get back up. There's no path for it to get back up. So the charges that were on the electroscope as the electrons went down into the ground is the charge that remains after I cut that. Is that okay? Can't remember who asked me for that question, but does it make sense? Whoever it was. Okay. And finally, we had question number 12 to go over here. If a glass rod becomes positively charged when rubbed with silk, use the law of conservation of charge to explain why the silk must be negatively charged. Here's a good little question for us. You rub silk against glass, the glass rod becomes positively charged. The silk becomes negatively charged. Why? Let's assume the glass and the silk are neutral to start off. Okay, neutral. Rub them together. Glass becomes positive 5. What's the total charge before I rub them together? 0, right. What's the total charge after I rub them together? 0. If the glass becomes positive 5, then the silk must become what? Negative 5, because the total charge afterwards has to remain 0. 5 plus negative 5 gives me 0. So the law of conservation of charge says the total charge has got to remain the same. If it starts off with 0, it's going to finish off as 0 as well. If I rub two things together, one becomes plus 5, the other's got to become minus 5. It's got to become opposite to that in order to keep the same amount of charge, in order to keep the charge as 0. Good? All right, the other bit of homework that we had last night was page 530, question number 1. Any issues with that one? That one's okay? Sure, sir? Okay. With this one, there's nothing huge that we have to circle here. It's probably not a bad idea to circle this negative, but in the end, we're not going to plug that negative into an equation anyways. We always drop the sign of a charge when plugging it into an equation. It's not a bad idea to circle it, just in case we need to find out whether it's attractive or repulsive, as we do in this question, because we do need that at that point. We want to find the force here. This is going to be R. This is going to be the distance that separates the electron from the proton, the distance between the two charges. This is going to be Q1. And this one is going to be Q2. And we're looking for, first of all, the magnitude of the force. So we're going to say F is equal to K Q1 Q2 over R squared. K is 8.99 times 10 to the 9. That's how we remember which force is bigger. Remember we said yesterday in class, when we were talking about these two forces, the electric force and the Newton's gravitational force, we said the electric force is bigger. This is how we remember that. Okay, if we're ever asked that question on a test and you start thinking, oh, I thought I had this. Which one was it that was bigger? I had this. I knew this. It's okay. You don't have to really remember it. Check your data sheet. Check the value of K, the constant for Coulomb's law. Check the value of G, the constant for Newton's law of universal gravitation. The gravity one is 10 to the minus 11. Coulomb's constant is 10 to the positive 9. If the electricity one is bigger, then the electricity force is also bigger. 8.99 times 10 to the 9 times 1.6 times 10 to the minus 19 times 1.6 times 10 to the minus 19. Divide that by the distance of 5.29 times 10 to the minus 11 meters. I can't tell you how many people over the years have gotten a question like this wrong because they forget to square the distance. Okay, it says KQ1 Q2 over R squared. Especially when we're dealing with a funny exponent like 10 to the minus 11, people just forget to square the distance for whatever reason. Even after I told that to my morning class, as I was still walking around, they were doing these problems, some more of these problems later on in the class, I still saw a couple people making that mistake. Even after I said, don't forget to square the distance. Okay? Learn from other people's mistakes. Everybody always says, learn from your own mistakes. Learn from your mistakes. Well, that's great. But it's better to learn from other people's mistakes and not make the mistakes to begin with. Okay? Don't make that mistake. Don't forget to square that distance. When we do the math there, we end up getting 8.22 times 10 to the minus 8 newtons. It tells us in the question that it's a force of attraction. How do we know that it's attraction? The equation doesn't tell me that anywhere. How do we know that it's attraction as opposed to repulsion? Yeah, opposite charges, yeah. We got a positive, we got a negative, and opposites attract. That's the first law of electricity, right? I'm going to do another example with you here, okay? The two spheres in the last example are momentarily brought together and then returned to their original separation distance. What's the electrostatic force now exerted by one charge on the other? I'm going to copy over question number 1, actually. And then I'm going to bring it over to that page just so we can see our data all together. So there's 10.1 above there. We want to use the data from 10.1 to solve this question. This shouldn't be that hard of a question, isn't it just the same answers we had in that last example? F is equal to KQ1 Q2 over R squared. 8.99 times 10 to the 9 times 2.1 times 10 to the minus 6 times 1.5 times 10 to the minus 6 divided by the distance is 0.030 meters squared. Isn't it the same thing? What's different about it? Obviously, there's got to be a difference, otherwise they wouldn't be giving me this question, right? What's different about it? Go ahead. Okay, they were brought together first. What difference does that make if they're brought together first? Conduction takes place, yes. And if conduction takes place, what's going to happen to them? They're going to transfer and B, starting with a B. The charges are going to balance. So let's deal with that touching first. Let's deal with that conduction first. We've got negative 2.1 times 10 to the minus 6 coulombs plus positive 1.5 times 10 to the minus 6 coulombs. We divide that by 2. We end up getting a value for charge there of, I think it's negative 0.3, isn't it? Times 10 to the minus 6. Is that right? Is that the charge on object 1 or on object 2? Or both, yes, good. It's the charge on both of them. So let's plug in my new value of charges, 8.99 times 10 to the 9, not times the charges that we had before in the last question, but the new charge that we have, 0.3 times 10 to the minus 6 coulombs, 0.3 times 10 to the minus 6 coulombs. Remember, they're both negative actually, but we're dropping the sign of the charge whenever we plug it into an equation. They're brought back to their original separation distance, so we're going to say 0.0330 meters. We square that. What do we get for the force now? I think in the last example, 10.1, I think it was 26 newtons. I think it's quite a bit smaller this time around. We do that, we end up getting 0.743 newtons. Is that a force of attraction or a force of repulsion, even though we're not asked that? Why is it repulsion, Rob? Good. They're both negative charges, and they're going to repel each other, so it's going to be a force of repulsion. Good. It's a much, much smaller force. A lot of people look at this and say, how can it be a much smaller force? Its total charge is still exactly the same. Yes, it is. But let's say I got this situation. I've got a charge that's minus 5 and a charge that's plus 5. There's going to be a pretty good force of attraction between them, right? If I touch them together, what do they become? 0 and 0. What's the force of attraction between them now? 0. So you can see how the force changes as the charges get redistributed. Just because we have the same total charge doesn't mean we have the same force. What matters is the distribution, what the charge is on each object. All right, see what you can do with that question. Page 531, please, for the next 60 seconds or so. All right, let's take a look at this one. Metal sphere with a negative charge, negative, first of all, of 3.00 microcoulombs, odd units there, 12 centimeters, also odd units, microcoulombs, odd units. We want to find the force. They touch each other. That's kind of important as well, that they touch each other, because that tells us that we're not going to use the charges that are given to us on the sheet. What's the force? All right. Let's first add them up and divide by 2. Let's get what the charge becomes, not what the charge was. When they touch each other, minus 3.00 microcoulombs and positive 2.00 microcoulombs average out to be what? I think it's negative 0.5. Negative 0.5 microcoulombs, or negative 0.50 times 10 to the minus 6 coulombs. So that's what the charges become after they touch each other. Add them up, divide by 2. Just average the two together. When you want to calculate the force now, using KQ1 Q2 over R squared, we're going to use those new values of charge, not the old values that were given to me in the question. But we're dropping the negative sign. Leave the negative exponent, but drop the negative sign on the base, which we always do. divided by r squared. R is 0.120 meters. I don't forget to convert that to meters because I see the centimeters circled up there in red. Don't forget to square that either. When you do the math on this one, I think you should get 0.156. It is a force of repulsion. We know that it's a force of repulsion because what? It was attraction initially, right? We had a positive charge and a negative charge before they touched together. But why is it a force of repulsion after they touch together? They both have the same charge. They both become negative 0.5 microcoulombs. I said in the last class, I said, look, you can always assume that when two objects touch each other, they're always going to repel each other after they touch because the charges are always going to balance out, right? To be either positive or negative. And somebody pointed out, what if they balance out to be neutral? +5 and -5 balance out to be neutral. Good point. If they balance out to be neutral, are they going to repel each other? No. So that's the only situation in which they wouldn't repel each other after two objects touch each other, is if they ended up being neutral after they touched each other. Okay? Otherwise, they're always going to repel each other. No, that's right. There wouldn't be attraction or repulsion. The force would be 0, right? If you think about it, the value of the force would be 0 because Q1 and Q2 would both be 0. So you can't really say attraction or repulsion when the value of the force is 0. All right, take a look at this one. Same type of thing here. Take a look at this one over the next minute or so, and then we'll go over it if we need to. All right, that seems to be good. The answer is 15.9 for that. Looks like people know what they're doing for that. If not, if you're having trouble with it, let me know, and we'll take a look at it, okay? Up until this point, we've fairly easily, I think, found the electric force between two charges. We'll call the two charges number 1 and number 2. Let's say that number 1 has a charge of 6 coulombs and number 2 has a charge of -3 coulombs. We can find the force that acts between those two fairly easily. F is equal to K Q1 Q2 over R squared, whatever the value of R is. What if we introduce a third charge here, though? A third charge that has a value of, let's say, 4.00 coulombs. Let's say this time we want to find the net force acting on number 2. The net force acting on number 2. It's a little bit harder than just solving the problems that we've solved until this point. It's not just a matter of K Q1 Q2 over R squared, because 3 has got to come into play here somewhere. These questions are much like the questions that we did last year with gravity. If you remember in Physics 20, I can remember one specific problem that Mr. Coderre's class and my class would have both done out of the textbook that had 3 objects, the Earth, the Moon, and the Sun in a row. And you wanted to find the net gravitational force on one of them due to the other 2. Do you guys remember that question? If you don't remember that question, it's okay, because we're going to focus on how to do it here today as well. But if you do remember it, it gives you a little bit of a leg up on this. In the end, what we've got to do is draw a free body diagram. A free body diagram for the one object that we're trying to find the net force of. Let's say in this case we're trying to find the net force acting on object number 2. There are 2 forces acting on object number 2. 1 is acting on number 2, and 3 is acting on number 2. I want to draw both of those forces. First force, 1 on 2. Let's pretend that object 3 isn't even there. Do 1 and 2 attract each other or repel each other? They attract each other. So there's going to be a force of attraction. 1 is going to pull 2 towards it. We're going to call that F12, the force of 1 on 2. Now, there's also a force of 2 on 1. 1 gets pulled to the right as a result of that force of attraction as well, right? But we don't really care about that force because the question was to find the net force acting on number 2. So although there is a force acting on number 1, we're going to ignore it because we're not trying to find the net force on number 1. Now let's ignore number 1. Is 2 and 3 an attractive force or a repulsive force? It's an attractive force. We know that because they're opposite charges. 2 is going to be pulled towards number 3 as a result of number 3. And 3 is going to be pulled towards number 2, but we don't really care about that one either because we're looking for the force on number 2 as opposed to number 3. Does that make sense? What do you think you'd do with this at this point if you wanted to find that net force? The net force acting on number 2. This is just like you spent probably 3 or 4 weeks on in Physics 20 doing various forms of this problem, where it was the net force is equal to all of those forces combined. F12 plus F32. The value of F12, we'd have to calculate using KQ1 Q2 over R squared. The value of F32, we'd have to calculate using the same equation. Then we'd add them up. But when we add them up, we have to make sure that we make F12 a negative value. Why would it be a negative value when we add them up? Rob? Good, because it's acting to the left. That's why we drew a free body diagram in the first place, right? Was to remind us, again, to remind us that we've got to make one of them negative. One's negative, one's positive. Calculate the values just using the equation that we've used. Get the values, add them up, but just make sure you pay attention to direction. That's it. That's it. It's really what we've just done over the last couple of days, yesterday and today, combined with what we spent a great deal of time on last year. Net force stuff equals the sum of the forces. Okay, I want to do a real problem here involving this type of thing. We have 3 charges here. Charge B that has a value of negative 2.10 times 10 to the minus 6 coulombs. It's placed midway between 2 similar spheres, sphere A and sphere C. The distance between A and C is 0.0330 meters. The value of sphere A is positive 1.00 times 10 to the minus 6. And the value of sphere C is positive 1.50 times 10 to the minus 6. We're trying to find the net force on the negative charge, so on charge B. Let's look at A and B, positive and negative, attractive or repulsive. It's an attractive force, so B is going to be pulled towards A. The force of A on B is to the left. Now, A is going to be pulled towards B, but we don't care, because that's not what we're trying to find here. Let's look at C and B, positive and negative, attractive or repulsive. It's attractive. If it's going to be attractive, if B is going to be attracted to C, then it's going to be pulled toward C. The force of B on C is acting to the right. Now let's get both of those forces. Let's get the values of those forces. The force of A on B is equal to KQA QB over R squared. 8.99 times 10 to the 9 times QA is 1.00 times 10 to the minus 6. What's the value of QB? 2.10 times 10 to the minus 6. Remember, we're dropping the sign of the charge there. Let's just finish this question off, okay? We're dropping the sign of that charge there. So it's negative 2.0, but we never plug that negative into an equation. The distance R is 0.0165. Good, because we want the distance there between A and B, not between A and C. Somebody have the value of that force? We get 69.34 newtons for that. We calculate the value of FCB. I think we can do this pretty quickly in our heads. It's going to be about 69. It's going to be about 104. About 104 point something. Is that right? When we go to combine them, we're going to say F net is equal to the sum of the forces FAB plus FCB. It's not hard at this point. We just got to recognize that FAB is which direction? It's negative. So we're going to say negative 69.34 to the left plus positive roughly 104 newtons. Is that what it works out to be? What is it? 145? Oh, the total you mean there? No, right here? Yeah, pretty sure it's 104 point something there. So when we add these up, what do we end up getting? Somewhere around 35? 34.68? Or 34.7 newtons. So the net force is positive 34.7 newtons, which means it's going to be acting to the right. Make sense? Rob, just take a look at that on your calculator again to make sure you get the right thing. But all right, your homework, the only homework that you have tonight is the practice problems that you see on page 533. 2 practice problems that go along with this, exactly the same thing as we see up here, okay? Page 533. Page 533.